Welcome back to the Quarterly Call. All content is for informational purposes and is not investment advice. Please consult with an investment professional. So we've gone through the source material from that keynote in Washington, D.C. It was billed, as focusing on industry, science, the future of computing.
Right.
But honestly, the scale of what they announced, the sheer number of partners involved,
Right.
it felt much bigger than just a product update.
Oh, definitely. It wasn't just an evolution. It felt like they were laying out a blueprint for a complete platform change across the board.
That's exactly it, a platform change.
And that's really the critical thing to grasp here. The material made it really clear this is a calculated shift, almost inevitable, driven by physics, really. The physical limits of transistors.
Right.
They weren't just talking faster chips. They were laying the groundwork for entirely new kinds of infrastructure. Stuff designed to basically work around the physical laws that have limited computing for, the last 50 years?
Okay, let's dig into that foundation then. Because for decades, everyone just assumed things would keep scaling predictably Moore's law, right?
Feel reliable.
But the sources are saying, look, that era, it's done, over. And that stagnation is forcing this really radical change in architecture.
Yeah, and the key point isn't that we can't physically cram more transistors onto silicon. We still can.
Okay.
The real problem is what happens when you actually power them up. The limit that really killed the old scaling model wasn't just transistor count. It was about power efficiency, about heat, something called Dennard scaling.
Dennard scaling. Okay, break that down for us. Why was that failing, nearly a decade ago, the real sort of death knell for the old way?
Well, Dennard scaling basically said that as transistors got smaller, you could also lower their operating voltage in proportion.
Right. Smaller and less power needed per transistor.
Exactly. So even though the chip got denser, the power consumption and the heat generated per square millimeter stayed roughly constant. It was beautiful while it lasted.
But it stopped lasting.
It stopped. We hit a wall where you couldn't lower the voltage proportionally anymore as transistors shrink. So suddenly, you pack more transistors on, and the power draw just shoots up, explodes, really, and the heat becomes completely unmanageable.
Ah, okay.
That's why CPUs had to go multi-core and start aggressively throttling performance. It basically proved the point for this, 30-year push towards accelerated computing. Using parallelism manages that heat and complexity totally differently.
So accelerated computing, using the GPU's parallel power alongside the CPU's sequential strength, it's not just a nice optimization anymore. It's basically the only way forward to get more computing power now.
Precisely. It's become the main path. But, and this is a huge but, it demands a completely different way of thinking about software.
Oh, so?
Well, the sources mentioned, if you take old-school sequential CPU code and just try to run it on a massively parallel GPU, it actually runs slower.
Slower, really?
Yeah. The code has to be fundamentally reimagined, reinvented for parallelism. You can't just port it over.
Which leads us straight to the bedrock, doesn't it?
Right.
The CUDA programming model. They really hammered home the strategic importance of CUDA, keeping it compatible, now up to CUDA 14, apparently.
Oh, absolutely central. That continuity, maintained over decades, that's what builds developer trust. It's a massive, massive commitment.
Right.
Think about it. If you're a developer spending, say, 3 years writing complex code, you need to know that code will still run on the hardware 10 years down the line.
You can't afford for the platform to just vanish underneath you.
No way. And that commitment, that stability, allows this whole ecosystem of specialized tools to grow on top. The real power isn't just CUDA itself, it's the, 350 plus CUDX libraries they mentioned.
Yeah.
Each one basically reinvents algorithms for a specific domain like science or finance or imaging to squeeze every drop of performance out of parallel processing.
And the examples they gave really show the kind of time and brain power involved. These aren't just quick code tweaks.
Not at all. Look at QLitho. Computational lithography. That took 7 years to develop. 7.
Wow.
It uses insane amounts of compute to simulate the physics of light needed to actually print the patterns onto silicon wafers for making new chips. And now, the big players, TSMC, Samsung, ASML, they're all using it. It's become critical infrastructure for the entire semiconductor industry.
So it accelerates the making of the very things that accelerate everything else.
Kind of mind-bending, isn't it? And they're doing the same thing in other areas, like logistics, supply chains, with QOpt.
Right, QOpt, tackling optimization problems.
Yeah, numerical optimization. They specifically mentioned the traveling salesperson problem, which sounds simple but gets incredibly complex at scale. We're talking optimizing routes for millions of products, millions of customers, almost in real time.
Stuff that was just computationally impossible a few years back.
Exactly. And it's not just industry. In healthcare, they highlighted MONAI, apparently the #1 medical imaging AI framework in the world now, speeding up diagnosis, helping researchers.
So the platform is really broad. It touches everything from making chips to understanding human health.
That's the point. It's comprehensive. And that sets the stage for this next massive shift. They talked about the economic one, driven by AI.
Okay, AI. But before we dive into the AI architecture itself, they made a very direct point about energy, didn't they?
Yes, they did. Very explicit. An acknowledgement that the kind of growth they're talking about needs enormous amounts of energy. And they specifically thanked the administration for pro-energy initiatives.
That felt significant, not just a side comment.
No, it felt like recognizing a fundamental constraint. These AI factories, they're going to be huge power consumers. Progress literally depends on having enough accessible, reliable energy. It's part of the critical infrastructure now.
Okay, so with that energy context in mind, let's talk about how AI is changing the definition of software itself. The old IT industry, the multi-trillion-dollar one we've had for decades, was built on tools, right?
Correct. Think about it. Excel, Word, your web browser.
Yeah.
They were all tools. We, the humans, use them to do a task.
We were the workers using the tools.
Exactly. This new AI wave, it's fundamentally different. AI isn't the tool anymore. AI is the worker, or maybe the agent that uses the tools.
Okay, that sounds like a simple distinction, but the implication is huge.
Order of magnitude, huge, because it changes the market you're addressing.
Give us an example. Paint a picture of this AI agent as a worker.
Okay, look at something like Perplexity. You don't manually open Google, search for flights, then open Kayak, then open the airline site. Perplexity is the agent. It uses the web browser as its tool to do the research, compare the prices, handle the booking, all based on your request.
Right, it does the sequence of tasks for you.
Or think about software development. There's this AI agent called Cursor. It uses VS Code, the programming editor, as its tool. You tell it what you want, and it writes complex chunks of code for you. It's massively boosting developer productivity.
Okay, I see.
And the most obvious one, maybe, is the robotaxi. The AI chauffeur is the worker doing the driving. The car itself, that's just its tool.
So, okay, the old IT tools supported human labor within the, $100 trillion global economy. They sat underneath it.
Right.
But these AI agents, they're starting to perform the labor itself, directly tackling parts of that $100 trillion economy, helping with labor shortages, driving productivity directly.
Exactly. And that's why the demand for AI compute is just exploding. It's not just about cool tech demos anymore. It's about real economic work.
Which leads directly to needing a whole new kind of infrastructure. The AI factory.
The AI factory, yeah.
So what makes an AI factory different from, say, the big general-purpose data centers we've had for years?
Well, those older data centers were, like you said, general purpose. They stored files, ran databases, hosted websites, a bit of everything. An AI factory is hyper-specialized, laser-focused.
On what?
It's designed to produce one thing: tokens.
Tokens. Okay, that word came up a lot. What exactly are tokens in this context?
Think of tokens as the basic unit of computation for AI. The fundamental currency, maybe. Like the vocabulary the AI understands and uses. You could almost think of them like the intellectual equivalent of barrels of crude oil coming out of a refinery.
So, raw material for intelligence.
Kind of, yeah. Raw material that gets refined into intelligent output.
Yeah.
And it's the efficiency of producing these tokens that matters.
And the real power here is that you can tokenize almost anything, right?
Yeah.
Not just language.
That's the beauty of it. We obviously tokenize words in English or other languages, but the same concept applies to pixels in an image or frames in a video. You can tokenize complex 3D structures like the layout of a physical factory floor.
Wow.
You can tokenize chemical compounds, protein sequences, genes, even patterns of motion or behavior, like how a robot arm moves.
So once you turn something into tokens, it becomes a kind of universal language that AI can process.
Exactly. It becomes standardized input. The AI can understand it, learn patterns from it, manipulate it. Doesn't matter if the final output is a chat response or a new drug molecule design or a robot's movement plan. It's all built from these tokens, and the goal is to produce them as cheaply as possible.
Okay, so we have this factory producing tokens. What's driving the demand for all these tokens? They mentioned two exponentials.
Right. Two big forces pushing demand sky high.
Let's take the first one. the scaling laws, the sheer complexity needed to make models smarter.
Yeah, they broke down the learning process into 3 stages, all needing massive compute. Stage 1 is pre-training. Think of this like basic schooling for the AI. It's about memorizing vast amounts of data and learning to generalize patterns, building foundational knowledge.
Okay, the basics.
Stage 2 is post-training. This is often where things like RLHF reinforcement learning with human feedback come in. You're teaching the AI specific skills, how to reason, how to code effectively, how to follow complex instructions, solve multi-step problems. It's like teaching it a trade or a profession.
And the third stage, this seemed like the really compute-intensive one, thinking or inference.
Yeah, and this is huge because it's the ongoing load. The speaker directly pushed back against the old idea that inference is, cheap or easy compared to training.
Right. People used to say training is hard, inference is easy.
And they argued, look, thinking isn't easy. Maybe regurgitating something you memorized is easy, but actual thinking, that involves constantly checking against real-time knowledge, doing research for the user, reasoning on their behalf for every single interaction.
So every time you ask the AI a question, it's doing a lot of heavy lifting in the background.
An extraordinary amount. And that puts this perpetual massive load on the infrastructure. It demands huge compute power constantly for every user.
Yeah.
So inference is definitely not easy or cheap at scale.
Okay, that's exponential. Number one, the models need more compute just to get smarter and think effectively.
Yeah.
What's the second exponential?
That's the virtuous cycle. It builds directly on the first one.
How so?
Because the models have now gotten smart enough, thanks to all that compute invested in pre-training and post-training, that they're actually commercially valuable. People are willing to pay for them.
Right. Companies licensing them, consumers subscribing.
Exactly. Think OpenAI, Perplexity, Cursor, all these services generating real revenue. And, crucially, that revenue gets plowed back into building more AI factories, buying more compute.
Which makes the models even smarter.
Which makes them more valuable, attracting more users, and more revenue.
Which funds more compute. Okay, I see the loop. It feeds itself.
It's a positive feedback loop, spinning faster and faster. Smarter models justify the cost. Paying users drive usage. Usage demands more compute makes smarter models. Round and round it goes.
So you've got these two immense pressures, the internal complexity of the AI itself and the external success of the business model, both screaming for more and more computation.
Right when traditional physics, Moore's law, and Dennard scaling basically said, nope, can't scale like that anymore.
That sets up a heck of an engineering challenge.
It's the central dilemma, really. The existential engineering problem. How do you keep delivering exponential compute growth when the old rules don't work?
And the answer they presented is extreme co-design.
Extreme co-design, which basically means throwing out the old way of designing things sequentially, chip first, then system, then software.
You can't optimize one piece at a time anymore.
No, you have to start with a blank sheet and re-architect everything at the same time. The chip, the system it sits in, the networking, the software stack, even the AI model architecture and the final application, it all has to be designed together holistically.
A full stack revolution, as you said earlier.
It really is. It's the only way they reckon they can get these massive generational leaps in performance now.
And the prime example of this co-design philosophy is the new Blackwell architecture, specifically the GB200 NVL72 system.
That's the flagship example, yeah. And the key thing about the NVL72 is it's not just a faster chip you slot into an existing server. It's conceived as a single giant computer that is the entire rack.
An entire rack is one computer.
Essentially, yes. It packs 72 Blackwell GPUs, which are themselves composed of 2 dies, so 144 GPU dies in total, all interconnected with extremely high bandwidth NVLink fabric, designed to function as one massive, unified virtual GPU.
Okay, and the performance claim was pretty startling. 10 times the performance of the previous generation, the H200.
A 10x generational leap, that's the shock they talked about.
But how do you get 10x the performance when physically the transistor count or silicon area hasn't increased 10x? It feels like, I don't know, bending the rules of physics.
Well, it comes down to that co-design, focusing specifically on what these huge modern AI models actually need. So yes, they increased the silicon area, added more transistors, but that's only part of it.
Okay.
They massively increased things like on-chip cache. They dramatically sped up the NVLink interconnect between the GPUs within the rack. They clearly identified that communication between all those GPUs was becoming a huge bottleneck.
So they designed the system, the rack itself, to minimize that communication latency.
Exactly. They treated the whole rack of 72 GPUs almost like components on a single board, slashing the time it takes for them to talk to each other. Plus, they put in specialized processing cores improvements to what they call the transformer engine, specifically optimized for the kind of complex math needed by these next-gen AI models, particularly for inference.
So the 10x jump isn't just from the chip. It's from optimizing the chip, the interconnect, the system, and the software stack all together for that specific AI workload.
That's the essence of co-design. And the most critical outcome, the metric they emphasized, is the economic one.
Which is?
Even though this NVL72 rack is undoubtedly a very expensive piece of kit, the sheer efficiency gain from that 10x performance means it produces the lowest cost tokens in the world.
Back to the tokens. Lower cost per token.
That's the key. By aggressively driving down the cost of producing intelligence, they make sure that virtuous cycle we talked about doesn't hit a wall because it's too expensive to run. It keeps the exponential growth going.
Okay, so you scale up performance within the rack with Blackwell. But AI factories need to scale out, connecting potentially thousands of these racks. That needs networking, right?
Absolutely critical. And not just any networking. You need specialized network architecture built for AI's unique demands. Inside the factory, connecting the racks, they talked about Spectrum X Ethernet.
Designed specifically for AI traffic.
Yeah, it handles the kind of massive, often bursty data flows you get during AI training and large-scale inference, much better than traditional Ethernet. And then when you need to connect multiple AI factories together, potentially across regions,
Gigascale factories.
you use Spectrum XGS or gigascale networking. Think of these networks as the central nervous system or the circulatory system of the whole AI infrastructure. Without them, these giant interconnected AI models would just starve or choke on data.
And looking even further ahead, they didn't stop at Blackwell. They introduced the next generation, the Vera-Rubin system.
Yeah, the third generation of this rack-scale computer concept.
Right.
It shows they're committed to this architectural roadmap for the long haul, the target they mentioned. 100 times the performance of the DGX-1, the system they delivered to OpenAI almost a decade ago.
100x leap over roughly a decade. That's staggering.
It is, and the physical design goals alone are ambitious. They're aiming for a system that's completely cable-less internally and 100% liquid-cooled.
Cableless and fully liquid-cooled. Why?
To handle the incredible power density and the sheer speed of data transfer required, at that scale, traditional cabling becomes a massive bottleneck and cooling nightmare. Liquid cooling is much more efficient for removing that much heat concentrated in one place.
They also talked about new types of processors needed within these future systems, identifying new bottlenecks in the AI process itself, like BlueField-4. Why is that needed?
Right, so as AI models get smarter and handle more complex tasks, their memory or context needs grow exponentially. Yeah, think about a long chat conversation with an AI. For the AI to give a relevant answer now, it needs to remember and process everything you talked about earlier. That history is the context.
Okay.
And retrieving and processing all that previous context, it's technically called KV caching, key value caching. It takes time and compute. You might even notice it yourself. Sometimes a chatbot gets slower the longer the conversation goes.
Right. It seems to take longer to think.
That's the KV cache bottleneck hitting. It's rapidly becoming a major performance killer for advanced AI inference. So BlueField-4 is this new kind of processor, a DPU, data processing unit, specifically designed to handle that context processing and caching workload efficiently, taking the burden off the main GPUs.
So it keeps the AI responsive, even when dealing with huge amounts of history or information.
Exactly. It's designed to solve the memory and latency problem for the thinking stage of AI, keeping response times fast.
And connecting all these different processors, the GPUs, the BlueField DPUs within the rack, is the NVLink switch.
Yeah, think of that as the ultra-high-speed internal spine or fabric connecting everything together. The comparison they used was pretty striking.
What was that?
They said the bandwidth provided by just one of these NVLink switches is several times the peak internet traffic of the entire world.
Several times the entire internet's peak traffic.
Yeah.
Inside one switch.
Yeah. It gives you a sense of the colossal amount of data flowing internally just to coordinate, say, 144 GPU dies working together as one giant brain. That switch ensures data moves almost instantly between every single processor, eliminating communication as a bottleneck within the system.
Okay, let's shift gears from the guts of the AI factory to some of the new global infrastructure frontiers they discussed. Starting with 6G wireless. This was framed quite significantly, wasn't it? Almost geopolitically.
It definitely was. There was a clear emphasis on the need, or maybe the opportunity, for the U.S. to reassert leadership in wireless by defining 6G, especially given that a lot of current 5G infrastructure relies on foreign technology.
And the key is making the network software-defined and programmable.
That's the core idea. They announced a new product line called NVIDIA ARC, which stands for Aerial Radio Network Computer.
Okay, ARC. What is it?
It's basically a combination of their latest chips, the Grace CPU, Blackwell GPU, and ConnectX networking, all running a specialized software library called the Aerial CUDX library. It essentially transforms the cellular base station from a fixed function box into a powerful, programmable, AI-capable computer.
Turning the cell tower into an edge supercomputer almost.
Pretty much. And the big validation was the partnership they announced with Nokia.
The world's second-largest telecom equipment maker.
Right. Nokia is committing to rewrite their software stack to run on ARC, making ARC the foundation for their future base stations. And importantly, it's designed to be compatible with their existing AirScale infrastructure.
Which means there's a huge potential upgrade path for millions of existing cell sites worldwide.
Exactly. It opens the door to deploying 6G capabilities and, crucially, integrated AI across the existing network footprint.
And this new programmable base station enables two major applications, they said.
Yeah, two big ones. First is AI for RAN, the radio access network.
AI optimizing the network itself.
Precisely. Using AI to constantly optimize how the radio signals are used, adjusting beamforming, managing interference, allocating bandwidth dynamically based on real-time traffic, weather conditions, user movement.
That sounds like it could make the network much more efficient.
Hugely efficient. They estimated that improving this spectral efficiency could save somewhere between 1.5% and 2% of the world's total power consumption.
1.5% to 2% of global power, just from optimizing radio waves. That's incredible.
Massive number when you scale it up. That's the power of AI optimization on critical infrastructure.
Okay, that's AI for the network. What was the second application?
The second one is AI on RAN. This is about using the base station as a compute platform.
Creating a new kind of cloud.
Essentially, yes. Just like Amazon built AWS on top of the internet infrastructure, the idea here is to leverage these newly powerful AI-enabled base stations out at the edge as compute centers. They specifically talked about creating an edge industrial robotics cloud.
Putting massive compute power right where factories and robots need it.
Exactly, for things like industrial automation, remote sensing, autonomous systems, applications where you need incredibly low latency, like microsecond response times, which you just can't get by going back to a distant cloud data center. The base station becomes the local brain.
Very interesting. Okay, let's switch to another frontier. Quantum computing. They mentioned a pretty fundamental breakthrough here.
Yeah, after decades of struggling with the stability problem of qubits, the breakthrough, they said, was the recent creation of the first truly coherent, stable, error-corrected logical qubit.
Okay, logical qubit versus physical qubit. What's the difference?
So for years, individual physical qubits have been incredibly fragile. They decohere, lose their quantum state almost instantly due to environmental noise. They're just too unstable to do complex calculations reliably.
Right.
A logical qubit is different. It's built using many, maybe tens or hundreds of these fragile physical qubits working together. Some qubits hold the data, while others are constantly running complex error correction algorithms in real time to detect and fix errors, essentially filtering out the noise to maintain the true, stable quantum state of that single logical qubit.
So you use many unreliable parts to create one reliable whole.
That's the idea. But achieving this breakthrough immediately created a new, maybe non-obvious problem or requirement.
Which is?
The quantum computer can't really work in isolation. The future, they argued, is hybrid quantum computing.
Hybrid, meaning quantum and classical working together.
Exactly. The quantum processing unit, the QPU, is amazing for certain types of calculations that are impossible for classical computers. But the sheer amount of conventional computing needed constantly for the error correction, for calibration, for running parts of the problem classically alongside the quantum parts, that has to be done by a powerful GPU supercomputer working hand in glove with the QPU.
And the timing has to be perfect.
Absolutely critical. If there's even a tiny delay more than microseconds between the QPU doing its thing and the classical computer doing the error correction or feeding it the next step, the logical qubit collapses. The whole calculation fails.
So that explains why they need specialized links and software.
Precisely. They introduced NVQLink as the high-speed, low-latency physical connection between the QPU and the GPU's supercomputer.
Hmm.
And CU2 is the software side and extension of the familiar CUDA model that lets programmers coordinate calculations and data movement between the quantum and classical processors seamlessly within those critical microseconds.
It bridges the quantum and classical worlds.
Yeah, it makes that essential tight coupling possible.
And this hybrid approach seems to be getting buy-in.
Apparently so. They listed support from 17 different quantum computing hardware companies and, significantly, 8 major U.S. Department of Energy labs, places like Berkeley Lab, Los Alamos, Oak Ridge, the big science centers.
And the DOE is building new machines based on this.
Yes, they announced a partnership to build 7 new AI supercomputers specifically designed for this hybrid quantum architecture. The goal is to accelerate U.S. scientific discovery by combining traditional physics simulations and robotics with the power of AI augmentation and, where appropriate, quantum computation.
Okay, let's pivot now to physical AI, where all this digital intelligence meets the real physical world. And they started this section with a strong nod to domestic manufacturing, right?
They did. The CEO referenced a request from President Trump about bringing manufacturing back to the U.S., and then pointed out that just 9 months later, the new Blackwell chips are in full production in Arizona and Texas.
Setting the stage for a discussion about reindustrialization powered by AI.
Exactly. It framed the whole idea that building and operating these advanced physical AI systems, robots, automated factories, autonomous vehicles, requires a specific stack of technologies, and that stack can drive domestic manufacturing.
And they defined 3 specific types of computers needed for this physical AI stack.
Yeah, 3 essential components working together. First, you need the massive training computer, like the Blackwell NVL72 racks, to teach the AI models the general skills and knowledge.
Okay, the big brain in the data center.
Second, you need the simulation computer. This is the Omniverse platform, which acts as a digital twin of the real world. This is where the AI agent learns the laws of physics, cause and effect, how to interact with objects, all in a safe virtual environment before it ever touches physical hardware.
Learning by doing, but digitally.
Right. Much faster and cheaper than learning purely through real-world trial and error, especially with expensive robots. And third, you need the operation computer. This is the embedded system, like the Thor chip for vehicles or the Jetson platform for robotics that actually runs the AI on board the robot or machine out in the physical world.
Training, simulation, operation.
And the crucial link is that all 3 run on the same underlying CUDA platform. So skills, models, data can flow seamlessly between the training environment, the simulation, and the real-world deployment. It's a unified pipeline.
Let's focus on that simulation piece, the digital twin Omniverse DSX. What is that exactly?
Omniverse DSX, they called it the data center or supercomputer experience, is basically the operating system or the digital blueprint for building and running these huge gigascale AI factories and also the factories producing physical goods.
Its main advantage is co-design again.
Yes, enabling the co-design of the physical and digital aspects. It lets you design the building itself, the power delivery, the cooling systems, the physical layout simultaneously with the AI compute infrastructure stack that will go inside it.
Why is that so much better than just building a shed and sticking racks in?
Because at the scale and density of these AI systems, power and cooling are the absolute limiting factors. Using Omniverse DSX, partners like Jacobs Engineering, Siemens, Schneider Electric can build a highly detailed digital twin of the entire facility first.
Simulate everything before pouring concrete.
Exactly. Simulate complex airflow for cooling, map out power distribution to avoid hotspots, optimize the placement of racks for maximum density and efficiency, all digitally. They claim this drastically cuts down design and build times and gets the factory operational, generating revenue much faster.
And the digital twin doesn't just disappear once the factory is built.
No, it stays active. It becomes the operational intelligence layer for the physical factory. AI agents, which were initially trained in that digital twin environment, can then be deployed into the physical factory.
To do what?
To actively optimize operations in real time. Things like managing power consumption dynamically, load shedding to reduce strain on the grid during peak times, optimizing cooling systems. They suggested this operational efficiency, managed by AI via the digital twin, could potentially add billions in revenue annually for just one large AI factory by maximizing uptime and minimizing energy costs.
And we're seeing big companies adopt this digital-first approach for physical manufacturing too. to tackle things like labor shortages.
Yeah, the Foxconn example in Texas was key here. They're building a highly automated robotics facility that was born digital in Omniverse.
Meaning designed entirely in simulation first.
Right. And they're using AI developed and tested in that simulation to manage the real-world assembly lines, the logistics within the factory. They even use Vision AI agents, AI for visual inspection and monitoring, also trained in the digital twin, to oversee operations and even act as interactive AI coaches to help onboard new human workers faster.
So the factory itself becomes a kind of robot, orchestrating other robots and augmenting human workers.
That's a good way to put it. It addresses both the lack of available labor and the skills gap needed for these advanced manufacturing environments.
And looking beyond factory robots, the potential for general-purpose humanoid robots seemed like a major focus.
It did. The sources speculated that humanoid robots, mentioning Figure AI specifically, which NVIDIA supports, could potentially become one of the largest markets ever for both consumer electronics and industrial equipment, rivaling the scale of things like the auto industry or personal computers eventually.
A huge potential market.
And beyond humanoids, they showed other examples. Agility robotics for warehouse automation, Johnson & Johnson using their tech for new, non-invasive surgical robots promising incredible precision.
They also showed that Disney robot, Blue, that wasn't just CGI, was it?
No, that was presented as a physics-based simulation running in Omniverse, using a framework called Newton.
Newton?
Yeah, Newton is the physics engine within Omniverse. It ensures that when an AI is being trained in simulation, like teaching that robot how to grasp objects or interact with its environment, it's learning based on realistic physics. Gravity, friction, inertia, all accounted for.
So it learns skills in simulation that actually transfer reliably to the real world.
That's the goal. Learning physically grounded skills much faster and safer than pure real-world training would allow.
Okay, last piece of physical AI mobility. The robot on wheels. Robotaxis, they said this is at an inflection point.
Yeah, the AI chauffeur concept finally seems ready for prime time, or close to it. And to help standardize and scale deployment globally, they highlighted the NVIDIA Drive Hyperion platform.
What is Hyperion?
It's basically a standardized, production-ready, safety-certified computing platform and sensor suite for robotaxis. It's designed to be built directly into vehicles by major automakers. They mentioned Lucid, Mercedes-Benz, Stellantis were adopting it.
So a common hardware foundation.
Exactly. And that standardization is key. It means different companies developing the actual autonomous driving AI software like Wave, Aurora, Neuro, who were mentioned, can deploy their AI systems onto this common, robust, sensor-rich platform without each having to reinvent the complex vehicle hardware and safety systems every single time.
It decouples the AI brain from the car body in a way.
Pretty much. It accelerates deployment for everyone, and then they connected it to the network.
The Uber partnership.
Right. Connecting these standardized, Hyperion-based intelligent cars into Uber's global ride-hailing network. This effectively creates a massive interconnected computing platform on wheels, ready for large-scale commercial robotaxi services.
Okay, the technology picture is immense. But what about the business side? Did the momentum described match the scale of these announcements? The growth visibility numbers sounded frankly incredible.
They're staggering. They stated they have visibility into $500 billion, $0.5 trillion of cumulative business for Blackwell and the early stages of Rubin, just through 2026.
$500 billion.
And this is important. They specify that number excludes China and the rest of Asia, so the actual global figure would be even higher.
It's hard to get your head around.
Yeah.
How does that compare to previous generations?
They put it in context. That represents 5 times the growth rate they saw with the previous generation, Hopper, in its first 5 quarters after launch. 5x growth on an already large base. The amount of capital pouring into this accelerated computing platform shift right now is just historically unprecedented.
And where's most of that money coming from initially? The big cloud providers.
Primarily, yes. The top 6 cloud service providers, Amazon, Google, Microsoft, Oracle, Meta, etc., are all massively increasing their capital expenditures. But here's a really interesting nuance they pointed out.
What's that?
The investment isn't just about running large language models or generative AI, though that's obviously a huge driver. It's being driven by the more fundamental shift away from general-purpose computing towards accelerated computing for all kinds of workloads.
Explain that distinction. Why accelerate if it's not AI?
Well, even before the deep learning explosion, there was a growing need to accelerate traditional but computationally heavy tasks. Things like massive data processing, complex scientific simulations, financial modeling, genomics analysis, even common machine learning algorithms like XGBoost.
Yep.
These all run much, much faster on GPUs than on CPUs. So their argument is, look, you CSPs are already having to re-architect your data centers for accelerated computing anyway, just to handle these demanding traditional workloads efficiently. And if you're making that fundamental architectural shift, the GPU platform, specifically NVIDIA's with CAI, is the most comprehensive and versatile solution.
As opposed to building specialized chips, ASICs, just for AI.
Exactly. An AI-specific ASIC might be super efficient at running one particular type of neural network, but it probably can't accelerate your massive SQL database queries or run complex physics simulations or handle the thousands of other algorithms developers use.
It's too specialized.
Right. The GPU, powered by all those COX libraries, offers the flexibility to accelerate the entire spectrum of workloads. So for a CSP making these huge, multi-billion-dollar long-term infrastructure bets, the GPU represents the safer, more versatile architectural choice. It covers both acceleration and AI.
Makes sense. Okay, beyond the giant CSPs, they also highlighted partnerships integrating this acceleration deep into core enterprise software, didn't they?
Absolutely. This shows the reach extending beyond the cloud into everyday business processes. Cybersecurity was a big one, partnering with CrowdStrike.
What are they doing there?
Creating AI-powered cybersecurity agents that can operate at speed of light, essentially using AI defensively to detect and respond to AI-driven attacks in milliseconds, both in the cloud and on devices. It's like pitting good AIs against bad AIs in real time.
Then there was data processing and intelligence.
Yeah, the partnership with Palantir Ontology, accelerating their platform to process and analyze massive data sets for business intelligence and national security applications at, again, extraordinary speed and scale.
Well,
Using AI to find the needle in the haystack instantly across petabytes of data.
and even the fundamental plumbing of global business.
That's where it gets really pervasive.
Yeah.
Integrating CDX acceleration libraries directly into major SaaS platforms like ServiceNow, which they said handles something like 85% of core enterprise workflows.
Cool.
And SAP, which is basically the financial operating system for maybe 80% of global commerce. So they're accelerating the fundamental software that runs the global economy.
That's embedding acceleration everywhere.
And even in niche, high-value areas. They mentioned working with EDA companies, Synopsys, Cadence, the guys who make the tools used to design chips to create AI ASIC designers, using AI to help design the next generation of silicon itself, effectively speeding up the entire innovation cycle in hardware.
Okay. So pulling this all together, it seems like the whole narrative ties back to two fundamental driving transitions.
That's exactly how they framed it. Two huge platform shifts happening concurrently. First, the unavoidable move, forced by physics, from general-purpose computing to accelerated computing. That's the hardware foundation changing.
Right.
Second, the equally massive paradigm shift in software, moving away from humans writing code for tools toward artificial intelligence itself being the worker, the agent, the creator.
Hardware shift and software shift.
And those two underlying transitions are the bedrock for everything else they announced. Whether it's the Arc platform for 6G, the Hyperion platform for robotaxis, or the Omniverse DSX platform for digital factories, they're all built on top of those two core shifts.
And this whole discussion, this structural change, it really seems to redefine what constitutes value, what drives national competitiveness maybe. We started off defining the AI factory as producing tokens.
Right. And if the core output of the modern economy is increasingly becoming intelligent data, these tokens, and the winning strategy is to build infrastructure that produces those tokens at the absolute lowest possible cost.
Then competitiveness isn't just about manufacturing physical goods or having cheap labor anymore.
Maybe not primarily. It suggests that national power and economic wealth in the coming decades might be defined more by a nation's capacity to generate intelligence, its AI factory capacity, which leads to a pretty provocative final thought for you, the listener. If computation is essentially becoming the raw material for intelligence, and the cost of producing that intelligence is dropping exponentially thanks to systems like Blackwell and this co-design approach, what does this really mean for the global balance of power, for national security, for economic disparity over the next 10, 20 years, when the means of producing intelligence becomes the key strategic asset?
A lot to think about there, a fundamental shift indeed. Thank you so much for tuning into the Quarterly Call. For more episodes, please remember to rate and follow our show. Until next time, stay curious and stay informed.